All right, somebody help me out. Where is the tangent positive?
Quadrant 1.
And?
Quadrant 3.
Yep, that's exactly right. The tangent is positive in 1 and 3 because tangent is y over x, and in quadrant 1 they're both positive, and in quadrant 3 they're both negative. So when you put y over x, you will get a positive number. Okay? So tangent is 1 over 1. So I recognize that triangle. This is what kind of a triangle here?
45.
It is. So this is a 45-degree angle. Now, I'm supposed to be answering in radians. So have you kind of just, I hate to say memorized because you didn't do it consciously, but just by doing all these problems, what's 45? Pi divided by what? It's pi divided by 4. It's pi divided by 4. Because if you do pi is to 180 as x is to 45, you end up dividing 180, 45 into 180, and it goes 4 times. So guys, I am not going to go through this process every time. If you need to do that, that's okay. But by this point, you should be recognizing that 45 is a fourth of 180. If you don't, it's fine, you're going to do this, but I'm not going to do that anymore. We're going to move past that. So my first quadrant angle is pi over 4. Now, I also, as you said, have a third quadrant angle. And in fact, I'm not even going to label that 45. I'm going to go ahead and label that pi over 4 since I'm supposed to be in radians. So what would be the measure of this big black angle here coming all the way around to here? Well, remember, from here to here is 180, and I'm going it's pi, and I'm going 1/4 more. So this is like pi plus a fourth. So the other answer to the problem is 5 pi over 4. 1 1/4 pi. Pi and an extra fourth. So here are the two answers to the problem. So our strategy to doing these problems by hand, first of all, if I'm doing them by hand, I'm always going to get special angles. So it's always going to be 30 pi over 6, 60 pi over 3, or 45 pi over 4, some combination of that. Once I figured out what quadrant I'm in, and I get that from paying attention to what I've been given, then I can find my reference angle, which is pi over 4 in this case, and then figure out what the answers are. Now, we're going to do the same thing on our calculator. Do the exact same kind of problem. It says the tangent of x is 1.75, and the directions are the same. So we're solving this in radians. So first thing I'm going to do is make sure my calculator is in radian mode. Okay, so it's in radian mode. We got to make sure we've done that. And now we've got tan x equal to another positive number. So won't the angle be either in quadrant 1 or 3 again? Because that's where the tangent, y over x, is positive. Now, I could go ahead and label the sides of this triangle to get 1.75, but that's not a special triangle, so I'm not going to waste my time. I'm going to go to my calculator, and to find the angle, I use second tangent. That's how we find angles. Remember when we were looking at those word problems? Sometimes our variable was an angle, and when the variable is an angle on your calculator, you're going to do second tangent. So second tangent, 1.75, remember we're in radians, I got 1.05. So my reference angle is 1.05. So now I've got to decide what are the actual answers to the question. Well, remember, they always start here. The angles always start here. So the first one is right there. So the first one is 1.05. The second one starts in the same place, but it's got to go all the way around to this angle. The kind of slanted lines that are the hypotenuse lines, those are the actual angle. So we're going all the way around to here. How would I find that red angle? How would I find the measure of that? Well, how far is it from here to here? Pi. That's pi. And I'm going to add another 1.05. So pi plus 1.05. And that's 4.19. So the second answer of two answers, 1.05 and then 4.19.
I have a question.
Yep.
So we're still doing those in radians?
Uh-huh. That's what these directions mean. That's a radian measure right there. So if that were a 360, I'd be doing it in degrees. The directions generally tell you. And if not, then you either need to ask or do it however you want. But 2 pi is a radian measure, so we're going with radians. All right, the next one says cosecant is 7/3. Now, you know, because you've done a lot of those fill-in-the-blank type problems, that if the cosecant is 7/3, the sine would be what? Yeah. So I prefer to think about it like this because I have a button on my calculator that'll do sines. I do not have a button on my calculator to do cosecants. So sine equals 3/7. So where is the sine a positive number? Certainly in quadrant 1. Where else is sine, which is y over r, where else is that positive? Quadrant 2. Sine is positive in 1 and 2 because that's where y is positive and sine is y. Now, you can go ahead and label this just like before, but there's no point in that. This is not going to be a special angle. And so to find x, to find the angle, which is what I'm looking for, I'm going to do second sine 3/7. Anytime I need the angle, I'll use my inverse sine or my second sine button. So second sine 3/7, 0.44. So my reference angle, which comes straight from the calculator, is 0.44. My answers will be the blue angle, which is 0.44, and then the green angle, which is not 0.44. How will I find the green angle?
Pi plus 0.44.
Am I going past pi?
No.
No, so it won't be pi plus 0.44, it'll be pi minus 0.44. Because if I went all the way to here, that would be pi, but I didn't go that far. It's pi minus 0.44, because I didn't make it all the way to pi. So that would be 2.70. So the two answers to the problem are 0.44, that's your quadrant 1 answer, and then pi minus 0.44, 2.70. Does everybody understand where I made this switch right in the beginning? because I'm going to have to make it in this next problem too, because they tell me that the secant is -3/2. I am not going to be able to type that in on my calculator. So if the secant is -3/2, then the cosine is -2/3. So now I have a problem where the cosine is negative. So remembering that cosine is x over r, where will I draw my triangles if the cosine has to be negative?
Quadrant 2.
That's one of them. Certainly, x is negative in quadrant 2. So cosine is negative in quadrant 2. Where else?
Quadrant 3.
Yep, x is negative in quadrant 3. So the two answers to the problem are going to be this one and this one. You must start on the positive x-axis when you measure your angle. So we go around till we hit a diagonal line. So that blue one is the first one and the green one is the second one. Now, in order to know what those angles are, the blue one and the green one, I need to know what the reference angle is. Like over here, it was 0.44. I need to know what that angle is right there. So I'm going to go to my calculator and I'm going to type second cosine 2 divided by 3. Kids, please don't put the negative in. You've already accounted for the negative, okay? You've already accounted for it by drawing it in this quadrant. You want the reference angle. It needs to be an acute angle, so you need to put that in as a positive. So second cosine 2/3 is 0.84. So my reference angle is 0.84. Now I need to find the measure of my blue angle, which is not 0.84. 0.84 will not be an answer to this question. But I'm going to use 0.84 to get the answer. How will I calculate the blue one?
Pi minus 0.84.
Yep, pi minus 0.84. If you went all the way to this line right here where I'm pointing, you'd be at pi. You didn't get that far. You're before that. You're 0.84 before pi. So pi minus 0.84. What about the green one? How am I going to calculate the green one?
Plus 0.84?
Yep, pi plus 0.84. We're going 0.84 past pi. Pi is right here, and we went another 0.84. So then I just type those in my calculator, and that will be the answer. So pi minus 0.84, and that is 2.30. So one of them is 2.30, and the other one is pi plus 0.84, which is 3.98. So these are the two answers to the problem. So we do those two problems, those two parts, part 2A, or part 2 and part 3, we do exactly the same way. The difference is in part 2, all of your angles were like 30s or 60s or 45s. If they're not, then we need a calculator. But,
So when you're doing cosine -1 and you're putting 2/3 in there, can it not be negative?
no, you put in the positive, you need the acute angle. You've already taken care of the negative by putting it in these quadrants.
Okay.
It isn't going to be an issue with sine or tangent, but it's an issue with cosine. Because when you put it in, if you put the negative in, you're going to get 2.30, but then you have no way of getting the 3.98. So don't put the negative in. You've already taken care of it by drawing it in these quadrants. All right, you got your calculators out. We're going to do a little bit. 4.6 is really not a big deal for us. So we're not going to spend a ton of time on 4.6, just basically a couple of things. First, we have these weird variations of functions like y equals sine squared. Let's set up our calculator and see what we can look at here. So we're already in radians, which is good. Let's go to our window and let's let x be negative, or x min. Everybody's got a calculator out? Everybody's typing in what I'm telling you. X min, go to window, x min, negative 4 pi. And then x max is 4 pi. Now, as soon as you put in the pi's, it turns to decimals, no big deal. That's fine. That's fine. And then for our y's, let's let our y minimum be negative 1 and our y maximum be positive 1. And we're already set in radians, so that's good.
What was the x max again?
We're going negative 4 pi to positive 4 pi, negative 1 to 1. Now, let's type in the equation. Please make sure that you have parentheses around sine x. Because if you don't put parentheses in, what's going to happen? If you don't put in parentheses, what will the calculator do? It'll square the x. You want it to square the sine. So we're going to type in parentheses, sine x, close the parentheses, and square it. And hit graph. All right, so what shape did you get? Did you get anything that you might have expected? Or now that you've looked at it, does it sort of make sense to you?
Yeah.
Does it make sense to you that remember what the sine looks like? The normal sine has hills and valleys, right? What happens when you square something? Oh, that's supposed to
It just becomes hills.
It just becomes positive. So does it make sense to you that all of the hill, or all the things are now hills and there aren't any valleys in there? Because when you square it, it's positive. All right.
Wait,
Yep.
I don't see that. Was the window negative pi?
Negative 4 pi, positive 4 pi, negative 1, positive 1. You have to be in radians, and you have to type it in just like this. All right, now we're going to go on to the second one, which is a combination of a parabola and a sine function. So I'm probably going to have to make a slight window change there. Leave my x's alone, but let's change our y's, and I'm kind of winging it here. Let's change our y's to just negative 10 and 10. So leave your x's alone, and let's go to negative 10 and 10 and see if that's big enough. Let's type in this equation, x squared, regular x squared, plus 2 sine x. Oops, 2 sine x. That's not a very interesting picture. And actually, it's not going to get much more interesting than that. I've tried a couple of different combinations and it didn't seem to help. Yeah. So, what did we get? What picture did you get? I'm going to go back to my original window that I told you.
I got like a valley of some sorts.
Yeah.
In the middle.
It looks like there might be some kind of little squiggliness in here. Not sure. And then it just looks like that. That's interesting, but that's what it is. This certainly makes sense in terms of that picture. And if there is indeed some squigglies there, that would make sense because that's going up and down. But that's it. So, no big deal there. Just wanted to graph a couple of weird things. You'll never have to graph anything like that by hand. Notice, though, that when I set up my window, what is the normal period for a sine curve? Normal period for a sine curve?
2 pi.
Yep. So I went a couple periods on each side. I went negative 4 pi to 4 pi, so I get a little bit more than one period. What if I'd been in degrees? Would I have used that window for x if I'd have been in degrees?
No.
No, I would have had to use like negative 720 to 720. Remember, a revolution is 360 in degrees. So if you want more than one revolution, the numbers start getting big really, really fast. So that's why we graph in radians. It's easier, smaller, more manageable to graph in radians. Okay, next, number 2. Is it a sinusoid? Why or why not? And what is its period? Okay, let's look at the first one. We'll talk about what all this means. Y equals sine x minus 3 cosine x. Let's, just for fun, sketch this in the same window that we just used. So negative 4 pi to 4 pi and negative 10 to 10. And let's see if we can graph this and get a feeling for what's happening. All right, have you graphed sine x minus 3 cosine x? By the way, when you hit sine, you're going to get a parentheses that pops up. You have to close that parentheses after the x. And the same thing over here. That one's not so important because it's at the end of the problem, but this one's essential. You have to close that parentheses. Now, did you get a picture that looks like it repeats itself? Yep, you sure did. If you combine two periodic functions, this is a periodic function. Its period is 2 pi. This is a periodic function. Its period is also 2 pi. Remember, sines and cosines have a period of 2 pi, unless we put a coefficient in here, which we didn't. When you combine two periodic functions, you're going to get another periodic function. If the two functions or more, you can combine more than two, but if the periods of the functions you are combining are the same, as they are here, the period of this one's 2 pi, the period of this one's 2 pi, then it is a sinusoid. To determine if something is a sinusoid, you simply find the period of each of its component pieces, and if they match, it's a yes. If this one had been 2 pi and this one had been 5 pi, then the answer would be no. Now, if this one was 2 pi and this one was 5 pi, it would still repeat when you graphed it. When you add two periodics, you're going to get another periodic. A special kind of periodic function is a sinusoid. And that happens when these two have the same period. Now, obviously, if the period of this one's 2 pi and the period of that one's 2 pi, when I add them together, the period is going to be 2 pi. Remember, the period is how long it goes before it starts repeating. If this one repeats every 2 pi, and this one repeats every 2 pi, then obviously, when I put them together, they're going to repeat every 2 pi. So, is it a sinusoid? Yes. Why? Because the periods of its component pieces are the same. What is the period? Well, they match, so it's easy. There's no figuring out to do. It's 2 pi. All right, let's look at the next one, because they aren't going to match in the next one. What is the period of the first piece?
2 pi.
Yep. So this one has a period of 2 pi. What is the period of the second piece?
I think it's just pi.
It is just pi. The period of the tangent's pi. Now, they don't match, so it's not a sinusoid. Why not? Because the periods don't match. The periods of the two pieces that are being added together aren't the same. It is, however, periodic. Now, here's how you figure that out, and you may just be smart enough to know already, but here's how you figure it out. The first piece, this sine piece, starts at 0 and repeats every 2 pi. So it starts at 0, starts over again at 2 pi, starts over again at 4 pi, 6 pi, and so on. Remember, the sine curve starts at 0, starts over again at 2 pi, starts over again at 4 pi, and so on. That's what periodic means. It keeps repeating itself. Now, this one repeats every pi. So it starts at 0, starts over again at pi, and then at 2 pi, and then at 3 pi, and then at 4 pi. So every pi, the tangent starts over. That's what it means to have a period of pi. The first place that they both start over is the period of the composition of the whole thing. So, 0 doesn't count. What's the first place that they both start over?
2 pi.
Yep, so the period's 2 pi. If you were to graph this on your calculator, you would see at 0, it repeats itself at 2 pi, and then at 4 pi, and so on, forever and ever. All right, let's look at the next one. Hopefully, you can look at this and tell me it's not sinusoidal. Because isn't the period of the sine 2 pi? Yeah, these are both sines. So if you put a different number here and here, aren't you going to end up with a different period? Yeah, so it's not sinusoidal. The period of this one would be what? What's the period of this piece?
Pi.
Yep, 2 pi over 2, which is pi. And what's the period of this piece?
2/5 pi.
2 pi over 5. Yep, 2/5 pi or 2 pi over 5. Now, they're both periodic, so I'm going to have a period. I just don't know what it is yet. So I'm going to think about this for a minute. This one starts over every pi. So 0, pi, 2 pi, 3 pi. This is where it starts over. The function is starting over every pi units. This one is starting over every 2/5 pi. So 2/5, 4/5, 6/5, 8/5, 10/5. Now there's something special about 10/5. What's 10/5? Yeah. So the first place that they both start over. So I don't care if you list all these out or not. That's how I do it. But somehow you got to figure out the first place where both of them are starting fresh. They both start fresh at 0. This is where this one starts fresh, and this is where this one starts fresh. The first time they are both starting over is their period. So the period of this problem is 2 pi. That means if you graphed it on your calculator, whatever weird shape it has, it would repeat every 2 pi. All right, try this one. Again, they're both sines. So can you just say right off the bat it's not going to be sinusoidal? Yeah, because this one is being divided by 2 and this one is being divided by 3, so there's no way their periods are going to match. So see if you can find the period of the sum. It's not sinusoidal, but see if you can find the period of the sum, or the difference. I got 2 pi again. Anybody confirm that? I got some thumbs up. Anybody have a question about where I got 2 pi as the period of the whole problem? Okay, a couple more. Now, do you think this one's going to be sinusoidal?
Yeah.
Yeah, because you've got a cosine and you know the normal period of the cosine is 2 pi, but you're dividing it by 2 pi, so the period's 1. This one's same thing. The normal period is 2 pi, but you're dividing it by exactly the same thing, so they both are going to have the same period, so that is sinusoidal. It is a sinusoid. Now, if the period of this one's 1 and the period of that one's 1, then the period of the whole shebang is 1. It repeats, they both repeat every 1 unit. Okay. Now, if I were graphing this, I would absolutely have to get rid of that 2, factor it out. But I'm not graphing it, I'm only looking at the periods. So I know that the period of this is going to be 2 pi over 2, right? That coefficient right there divides the period. Now if I needed the phase shift and all that, I'd have to factor that 2 out, but I don't need all that. This is the only number I need to look at right here. And same over here. This is going to be, oops, the period is going to be 2 pi over 3. I think I had one like this earlier. I don't know.
Yeah, you did.
Did I? So anyway, it's not a sinusoid. We know that. The periods don't match. This one repeats every pi. And this one repeats every 2/3 pi. So the first time they overlap is right there at 2 pi, just like last time. So the period of the sum, or the difference, is 2 pi. Yeah, 2 pi. So those questions are easy. If you're a sinusoid, the 2 pieces, or you could have 3 or 4 pieces, these all have just 2, but all the pieces have to have the same period to be sinusoidal. If they don't have the same period, then you have to do a little work, a little thinking to figure out what the period is, but it's the first time they both start over. All right, that's all there is to 4.6. So your 4.5 and 4.6 homework are going to be due together, and that will be, what's today, Tuesday, that'll be Thursday. So your 4.5 and 4.6 will be due on Thursday. And now we're going to start 4.7. We will not get this done, but we're going to at least get it started. So I want everybody paying close attention, because if we don't pay close attention, this can get confusing. If we do pay close attention, it is super simple. This right here, I'm looking at problem number 1. This problem literally says to me, find the angle whose sine is √3/2. Find the angle. There's only one answer to this question. Your calculator would give you the answer, but we are going to do it without a calculator, and I bet you can see why these are kind of special numbers. Now, no matter what this is, this could be a tangent or a cosine, this could be anything. No matter what it is, if this number right here, look where I'm pointing, right here, this number right here, if it's positive, you are going to draw the triangle that contains the angle in quadrant 1. If this number is positive, regardless of the function, you're going to draw your picture in quadrant 1. This particular problem, this is the sine value. So the sine opposite over hypotenuse is √3/2. Again, the problem says, figure out the angle whose sine is √3/2. So opposite over hypotenuse is √3/2. Well, you should recognize that. What angle is that?
60.
Yep, in degrees, that's 60. It says do it in radians. So instead of 60, we'll say pi over 3, because 60 is 1/3 of 180. So the answer to the question, there's only one answer, and it's pi over 3, 60 degrees. Now, the very next question is pretty much the same, only the number is negative. See that? This says find the angle whose sine is -1/2. So I need you to write something down now. As long as the number here, right here where I'm pointing, this number right here, as long as that's positive, you're always going to draw your picture in quadrant 1. But when it's negative, when that number is negative, if it's a sine a tangent or a cosecant, you're going to draw it in quadrant 4. If it's a cosine, a cotangent, or a secant, you're going to draw it in quadrant 2. These rules come from the pictures, the graphs of the inverse functions themselves. We're not going to go into the graphs. You just have to remember what are called the principal values. That is, where do I draw my triangle? Where will my angles be? This is an angle. You need to know where it is if you're going to figure out how big it is. Since it's an inverse sine and it's a negative, so this all has to do with the inverse functions. If any of these inverse functions, these 3, you're going to draw your picture in quadrant 4. These 3, you're going to draw your picture in quadrant 2. So, since it's a sine and it's negative, I'm going to draw my picture in quadrant 4. These are the rules. Got to know them. Remember, if that number's positive, it's quadrant 1. You don't need to worry about it if it's positive. It's only if it's negative that we have these restrictions. Only if we have a negative number do we have these restrictions. All right, so I'm in quadrant 4, and I know the sine opposite over hypotenuse is negative 1/2, which means this side is root 3, which means how big is this angle right here? Yep, it's a 30-degree angle. I'm supposed to be answering in radians though, so instead of 30, I'll say pi over 6, because 30 is a 1/6 of 180. Now, is pi over 6 the answer to the question? No, because pi over 6 would be in quadrant 1. 30 degrees is in quadrant 1. If you want this 30-degree angle down here in quadrant 4, you're going to have to say negative pi over 6. Negative pi over 6. Okay? I want to show you something. Go back to your calculator. Change your calculator into degrees. Change your calculator into degrees and type in that problem. Second sine negative 1/2. What does it say? Change it to degrees. Type that in. What does it say?
Negative 30.
Exactly. Negative 30. Which is exactly what we got, right? We got it in radians, but negative 30 degrees is the answer to the question. Your calculator has memorized these rules. Your calculator follows these rules. When you're doing it by hand, you have to memorize the rules so that you get the same answer that the calculator does. All right, let's try the next one. This one's a positive number, so I'm just going to draw it in quadrant 1. And it says, what is the angle? Oh, is today the lunch period?
Yeah.
Oh, okay. All right. Well, good thing I looked up there. We'll go for a little bit longer and then we'll stop for lunch, okay? So, I'm looking for the angle whose tangent is 1. So, I want to know the angle that has a tangent of 1. Well, everybody out there should be able to tell me immediately that angle is how big?
45.
Yes, 45 degrees. So this is my answer. My answer is 45 degrees. But I'm supposed to be answering in radians. So instead of 45 degrees, I'll say pi over 4. because 45 is a fourth of 180. 180 divided by 4. And that's it. That's all there is to it. That's easy. All right, let's look at D. Uh-oh. I love to draw a picture of this, but there's going to be a little bit of a problem, isn't there? Can I draw a triangle that has adjacent over hypotenuse as 0 over 1, or 0? Can I draw a triangle with a side of 0? Nope. So what do I do? What?
You have to make a circle.
Gotta make a circle. That's right. Can't draw a triangle, gotta make a circle. And then you're gonna look around the circle until you find the places where cosine is 0 over 1. Now remember, the circle we drew has a radius of 1. That's a given. The radius is 1. So that's given. I'm looking for where x is 0. Isn't x 0 in 2 places? But this problem can only have one answer. Can you think about which of the 2 answers, this one or this one, makes perfectly good sense to use? Tyler? Are you pointing up? Yep. Tyler says this one. This is indeed the answer. The answer is going to be pi over 2. That's 90, or half a pi. Now, why did Tyler say that? Stop and think. If this had been a positive number, I would have drawn it in this quadrant. If this had been a negative number, it's a cosine, so I would have drawn it in that quadrant. So it makes sense that any answer I give is going to be in the top half of the circle, because that's where the 2 triangles are that are possible answers for an inverse cosine problem. Okay? All right. Let me see. What time's this period end? All right. Well, that's perfectly good timing. Oh, and that's good. We finished that little section. So we'll stop there. You guys can go to lunch, and you do not have to come back. Does anyone have a question for me? Nope. All right. Have a great day.
Thank you.
Bye.
Thank you.
Wake up, George. Oh, shoot.